Greetings from Spain. My name is Angel Lacal, and I'm here presenting this presentation from two main partners, CTAG and Stellantis, that I will present now in a minute. So CTAG, Research and Technology Organization in Spain. We are in this red dot here in the map, and well, we're focusing research, especially in the automotive industry. And the other partner is Stellantis, very well-known automotive OEM, you know, Peugeot, Citroën, and Fiat, and many other brands. So the collaboration comes from a factory in Spain. So the context is in manufacturing. Sometimes, very often, manufacturing processes provoke some kind of unwanted accumulations of material. We can think of a welding such as this, and it's usually necessary to remove or smooth these unwanted accumulations. So this labels very different things like finishing or smoothing or polishing or other processes known as machinings. Of course, we want to prevent the occurrence of this burst, but sometimes you cannot avoid it. And well, this is traditionally being performed manually, but you know, if you are a human operator performing this kind of labor, well, it's sometimes dangerous or sometimes it's inconsistent. Well, of course, you want to automate it. So in this contribution, what we are proposing is a new methodology to automate this kind of finishing processes in order to guide similar developments in the future. This involves many different technologies like mechatronics and electronics and software and many other things. And basically the thing is that if you need to adapt to a specific burst or unwanted accumulations, you need some kind of systematic procedure. We will present two use cases in which we have applied this methodology, and both of them have been implemented in a factory, in fact, more than one factory in Spain and China. And well, this will be the presentation at the end of these slides. So, well, the background comes from these unwanted accumulations of material, and the hypothesis is that they have geometries that you cannot predict. You cannot know the position or the geometry of these unwanted accumulations. So, of course, you need to recognize and inspect each of the parts. You cannot assume and perform a blind trajectory. Let's say you need to, by some kind of sensor, identify each of the specific parts you're going to that you're going to machine. And then the next step should be adapt some kind of predefined trajectory. So depending on what you find with the sensor, maybe you need to adapt your trajectory. And then, well, you have to define many things that we will see now in a minute as a finishing strategy. So very quick review of these technologies. Talking about sensoring, what we want to measure is some physical features by some kind of electronic instrument. We can have contact sensors or non-contact sensors. If we're talking of non-contact sensors, we are talking about machine vision, laser triangulation, or stereo vision. In any case, well, we need some kind of device to obtain this information to identify how the area to machine looks like. Then if we talk about the finishing technology, we are usually dealing with a robot, which allows us to react to any unexpected geometry. A 6-axis robot, industrial robot, usually allows to do that. And then, of course, we have to think of many things. I'm going to go very quickly with this, but of course, you want to perform the operation in this direction or in this other direction. Maybe the rotation can be in one sense or another, and everything has pros and cons. But in any case, many things to think about that. The finishing strategy, which is very important. Maybe in some cases, maybe we want to scan the part and then we want to develop again another trajectory to perform the finishing, which is option A. Or maybe we want to do both things at the same time, obviously first with a separation of some seconds, the sensoring and then the actuation. And of course, again, we have pros and cons. If we don't have much cycle time, maybe the option B is the good one. If we have enough cycle time in the manufacturing line, maybe option A is the good option. But again, something to decide in the process. And the control system, well, the tool itself, the machine that we are going to use to remove this unwanted material usually involves a motor, and this motor, of course, has a lot of features and a lot of characteristics that we have to define. And well, this is part of the control strategy that you have to involve in your system. So going directly to the point, the methodology that we have proposed and that we have followed in these use cases involves these 4 steps. First, measuring the part. Each part is potentially different. Then once we know the characteristics of the part that we want to address, we create a path, and this path will be followed by the tool used to perform the machining. Step 3, the operation itself of finishing, and step 4, verifying that the part reaches some quality threshold. If it's okay, the operation is finished. Otherwise, we need to measure again and finish again until we obtain the required quality. So in the first step, we want to use some sensor to measure the shape and the size of the unwanted material which has been accumulated. We have to select the sensor, and we have to decide which kind of sensor we want to use. In modern facilities, we usually use 3D machine vision sensors, but of course it depends on the case. On the step 2, once we know what is this underside material, which is the shape and its position, we usually have to modify some kind of predefined reference route. So we have some predefined route, and depending on the specific features of the material that we want to remove, maybe we need to adjust a little bit this route, this trajectory. Maybe we want to change the angle a little bit. And well, this is the path that the tool will recreate in the next step. And step 3 is the finishing operation itself. Once we know the path we have to follow, we just follow this path and we execute the operation, usually with a 6-axis robot. And of course, depending on the material we want to remove, it's not the same aluminum, that's steel, whatever. Well, we have to define which tool, which motor, etc., and the strategy that we want to follow. And part verification, usually some kind of machine vision system, quality control system, in which we measure if the quality that we are getting is sufficient or not. Sometimes we cannot repeat this indefinitely because we are removing material. Sometimes maybe if we repeat the process several times, we are causing some functional or structural problem. Let's imagine in a car part, maybe we are just removing too much material. So of course, maybe we cannot define this indefinitely. Okay, so this is the concept of the methodology that we propose, and the use cases that we will show how to apply this methodology is as follows. This is a part in the automotive manufacturing processes. This is the lateral part of a car, and instead of stamping one only part, which is the common thing to do in this project, they decided to split this lateral part into parts, and then in some part of the manufacturing process, you have to weld it. But the consequence of this welding is this accumulation of material, which is what we want to remove. And this was defined in this factory in Spain in 2 steps. The first step is a smoothing. The second step is a polishing, and the idea is after the two use cases, the 2 stages of this process, we have to go from the left image to the right image, which is a result that we can show to the customer. So that this is the result that then it's painted and it's incorporated in the car. So first step, smoothing. We want to have a result from left to right. Okay, so as you can see, we are removing the gross part of this burr, of this unwanted material. So to illustrate how we follow the methodology that we have presented some slides ago, in this case, because of the very short cycle time in this factory in Vigo in Spain, each 60 seconds a new car arrives from the manufacturing lines, so the cycle time is quite reduced. So we didn't have much time, so we have to follow the finishing while measuring strategy. So we cannot spend a lot of time measuring and then perform the operation. We had to do it on the same time. We used a robot. I will show some pictures now. And well, the basic idea is we have a predefined trajectory. We have sensors. Depending on what the sensors measure, we adjust the trajectory slightly. So the robot mounts this kind of tool, and we have two sensors, left and right, 1D sensors in this case. And what we measure is how the welding looks like. If the welding is deeper in one side and not on the other, we will measure difference on this kind of sensors. So the idea is that we adjust this angle, and instead of developing a trajectory like this, maybe we measure slightly the angle. And this is depending on these displacement sensors, which is the first step of the methodology part measuring. Well, here you see some pictures of the robot using this tool. Here we have a huge part that we have to process, and in this case we have the small area that we are modifying with the machining process. So in the path creation, what we are doing is adapting this predefined trajectory that I told you before, using this information from the sensors. The PLC is handling all the process, and well, since we need a very high precision, we are using specific calibration systems to calibrate the robot. I remember once in an hour or once every half an hour, there is a calibration system to have the better accuracy of the system. Then, well, specific details of the finishing operation, industrial robot EBB, well, specific motor, I will not enter into much detail, and a full set of components around 70,000 euros in this case. And there was no part verification because the end of this stage is the input for the second use case. So there was not a specific part verification. Instead, well, what we want to do is now start the polishing, which is the second use case. And in the second use case, what we want to achieve is from something like this, we want to have a polished surface. Again, same cycle time. Again, we have to do the finishing while measuring strategy. And in this case, well, in the first stage, we use a sensor which is mounted on the robot. This is not machine vision. This is the robot itself can feel, let's say, the force which is applied. So if the robot feels too much force, we can measure that force. And similarly to the first use case, we have a predefined trajectory, and depending on the force that this force sensor feels, we can change slightly the trajectory and adapt it to what the robot is feeling in this case. Well, not much into detail, but we have a predefined trajectory. Depending on these measures from the force sensor, we can adjust slightly the trajectory. And what we are looking for is to change the position of the tool and also the force that the robot is performing on the part, so that we try to adapt to what we feel on the part. Well, the system looks like this. In this case, it's a collaborative robot with a specific grinding material using 3M abrasive discs. And well, the idea in this case is to polish this zone 6 to 8 times until we reach the desired result. And basically, in this case, we did perform a part verification using a machine vision system from the company Size in Germany, which is optical non-contact, and it can measure bumps and surface problems using the Moire technique. Well, you can measure if you project some light on the part, and if the distance that you expect from these lines is not that you expect it, then the system assumes that there is some kind of bump, scratch, whatever. And this determines if the part is adequate for sending to the customer. Otherwise, the part can start again to be polished if necessary. Okay. Without the machine vision system, the set is around 50,000 euros. The machine vision system is much more expensive. I remember maybe 200,000, something like that. So, well, to sum up the results, we used the proposed methodology in 2 use cases, which are, as I say, consecutive. The first one is the smoothing and the second, the polishing. We reach an accuracy in both cases of 0.2 millimeters. And this accuracy is due to the robot, not due to the tools, but to the robot themselves. In the first case, it's a system that is in use, that was installed in 2012. It's been 10 years in use, and we have processed 500,000 cars. using the first system. We are saving a lot of material because all the material that we're removing is encased and it can be recycled. And we implemented a robotic cell in this factory in Vigo, Spain, and also in Wuhan, in China, a couple of years later. In the second use case, it was a proof of concept that was installed only during some months, and we only processed almost 20,000 cars. And the problem was, in this second use case, we couldn't reach, let's say, the expected quality that a human operator can get. It was very challenging. But in any case, it's an application of the methodology, independently of the success or not of the use case. It's an application of the methodology that we are trying to present and suggest in this contribution. And well, you can not only apply it to burrs and welding results, you could apply similar methodology in polishing in-painted surfaces or composites or fiber polymers. There are many industrial processes which can benefit from this methodology. And as a conclusion, well, is a set of steps that try to organize and guide finishing operations like this, based in these forming stages, which are quite obvious. Measuring the part, create a path to follow, finishing the part, and then checking if the part is okay. And well, we try to automate operations that are usually performed manually, and we believe that, well, it's useful to do it since we can especially avoid these human-related ergonomic issues due to the dust and the complicated this manual process. The main challenge is obtaining a good level of aspect quality and working in non-metallic surfaces. But again, this is not related to the methodology. You can use the methodology, and then every use case, of course, would be different and would be challenging. I want to acknowledge the funding institution in Spain that has funded this project some years ago. And well, I'm open to your questions. Thank you for your attendance. And please, if you have any question, I'm glad to answer.